All right. Hello, everyone. Welcome to the next lecture. So, in the in the previous lecture, we talked about the natural response of an RL circuit, resistor, and an inductor, and we derived various expressions and did an example problem as well. So, in this lecture, we are going to do something very similar, but we are going to derive expressions for an RC circuit, resistor, and a capacitor, and find the natural response for that. And also, we are going to do an example problem. Okay, so let's get started. Again, we are talking about a natural response of a circuit, right? A resistor with a capacitor in today's lecture. So, for example, consider the circuit. If you look at the circuit, so just assume that initially this switch was connected to position A, and what do we have? We have a voltage source, an excitation source, we have a resistor R1, and we have a capacitor. So when the switch was at position A, the capacitor gets charged, right? And this is what we studied in the very first lecture, in the recap lecture, that if you are going to hook up a voltage source to a battery, let's say a parallel plate capacitor, right, the charges will get accumulated, and as long as there is a rate of change of voltage and a rate of change of the charging, there will be a current there. And we also learned that once a steady state will reach, right, whatever that transient, since it's a constant DC voltage source, right, since it's a constant DC voltage source VG, once that transient will be over and the VG is established, what would that do is the capacitor will be charged fully, and we will get open circuit, and the capacitor will be charged to a voltage of VG. Okay, great. So that's one part of the circuit. When the switch is at a position A, the capacitor will get charged, and as soon as at time equals to t equals to 0, we are going to move the switch to position B. As soon as the switch is moved to a position B, the excitation source VG is out, right? And the resistor, of course, is out as well. So as soon as it is moved to a position B, the capacitor will start to get discharged. However, at that very instant of 0, time equals to 0, like the inductor opposes the changes in the current, the capacitor is going to oppose a change in the voltage, but eventually it will discharge. Okay. And essentially, this is a natural response of an RC circuit. So what we are going to derive an equation over here very shortly is we are going to learn that how this discharging will happen once it will move to position B. Okay. So this is what we already talked about, that the capacitor behaves as an open circuit in the presence of a constant voltage source once a steady state condition is reached. And we also talked about this when the switch, we are going to move the switch from A to B, right? Over here at time t equals to 0, the voltage on the capacitor is VG, right? Because there is no instantaneous change in the voltage across the capacitor. This is a very similar concept as we discussed in the last lecture in case of an inductor, where inductor won't allow an instantaneous change in the current. So at time t is less than 0, right, the voltage that was appearing across the capacitor was VG, because capacitor got fully charged to the voltage VG. As soon as you remove the excitation source and move the switch to position B, that voltage will remain over there, VG, for an instant, and then it will start to discharge. Okay, and this is what we are going to learn. So once we will do the switching at time t equals to 0, right, so t is equals to 0 greater than 0, this is a circuit what it's going to look like, right? So we have a capacitor over here and we have a resistor over here. So let's drive the equations for the circuit now. All right, so I'm going to drive some of the equations for the circuit. So let's kind of get started, right? So again, we are going to make some assumptions. So the one thing that I'm going to do is I'm going to call this voltage VG as V0 as well, because essentially what it's going to do is this VG represents the initial condition or initial voltage, or V0, or it represents a capacitor voltage at time t equals to 0, right? So essentially it represents the capacitor voltage at time t equals to 0, and also t equals to 0 negative, which we are going to talk about in a second. right? It is Vg, but it is also equals to V naught. So for simplicity, we are going to call it V naught. And similarly, let us also define the voltage across the capacitor more specifically as Vc of t, and define the voltage across resistor as Vr of t. And let's derive these equations. Okay. Okay, so at time t equals to 0, source is removed. This we already know that, right? And then we know that when the source was removed, the initial voltage for capacitor Vc at 0 was equals to V naught, and then the capacitor will discharge. All right, so let's find Vc of t for t greater or equals to 0. Okay, so let's find this thing. And I am going to highlight this because I'm going to use it. Okay, so essentially what I'm going to do is I'm going to apply a Kirchhoff's voltage law to the circuit. And essentially what we will get is we will get Vc of t plus Vr of t comes out to be equals to 0. Now we know that Vr of t equals I of t times R. So I am going to do Vc of t is Vc of t plus Vr of t is I of t times the resistance R. Okay, so if you remember, again in one of the recap lectures, we also talk about the IV relation for a capacitor. The IV relation for the capacitor is I equals C dV by dt. And again, this voltage is across the capacitor. This voltage is across the capacitor. So I can replace this I over here because you have the same current flowing in this loop. Okay, so we get Vc of t plus C R d Vc of t by dt. Okay, and of course this is equals to 0, this is equals to 0. Okay, so I am going to rearrange this just a little bit, and I'm gonna move this constant and this on the other side. dVc of t divided by dt equals to minus CR or minus RC minus 1 over RC and minus Vc of t and Vc of t. Okay, so dVc of t divided by, so you move this over there, and minus 1 over RC Vc of t. Okay, great. So I am going to further move this Vc of t on the other side and move d of t on the other side. So I would get 1 over Vc times dVc equals minus 1 over RC times dt. Okay. What I'm going to do now is I am going to take integrals on both sides. Let me go to the next slide. 1 over, let me rewrite this equation actually. Make the things easier. 1 over Vc dVc equals minus 1 over RC times dt. Okay, I'm going to integrate on both sides now. So we will integrate over here. And again, we are integrating with respect to the capacitor voltage. So our limits of integration can be from capacitor voltage at 0 to capacitor voltage at time t. Or we can always replace the variable of integration here as well. In case if we can also keep it if we want. Similarly, minus 1 over RC, we can take the limits of integration from 0 to t. Okay, so 1 over C We already did this analysis, a very similar analysis in the past lecture when we were deriving the equation for the current, and we already know that 1 over x dx would eventually comes out to be the natural log once we complete the integration. Okay, so I am going to do this. This is going to come out to be natural log of Vc of t divided by Vc at time equals to 0. This should be equals to minus 1 over RC times t. Okay, because essentially this thing would come out to be t minus 0. So essentially t. Okay, so how you can solve this, we already solved this again in the previous lecture as well, a very similar expression. So essentially what you do is you exponentiate both sides, right? So e times natural log of Vc of t over Vc of 0 equals e raised to power natural log of minus t over Rc, right? And we also saw that what this expression is going to look like, it's the whatever is the parenthesis of the natural log. So we are going to get Vc of t over Vc of 0 equals e raised to power minus t over Rc, and I am going to change this to Vc of t equals Vc of 0 e raised to power minus t over Rc. So there you go. This is an expression for the voltage across a capacitor. Since we already know that Vc of 0, we defined it was equals to Vg or V naught. So I can rewrite this expression as Vc of t equals V naught e raised to power minus t over Rc. So very easy expression to remember and very similar to what in terms of its form of what we saw for the inductor, right? So this is called a natural response of RC circuit. Okay, so let's find out again in the previous slide. Let's find out the value of this I. So value of the current is essentially this is, we have the current that is flowing into the loop. So similar current is going to flow through the resistor as well. So I can be equals to, for example, Vc divided by R. We already know the value of the Vc. Divided by R, V naught over R, e raised to power minus tau over Rc. So this is the value of the current that is flowing through the circuit. So we found the capacitor voltage, the circuit current as well, and we are going to define again the rate of the decay, right? And which we call it as a time constant. So time constant tau in an RC circuit equals to Rc, and this is going to define the rate of decay. Rate of decay. So essentially, this equation states that, or just by the looks of it, that as soon as I am going to take out the excitation source from the RC circuit, the instantaneously V naught will still remain there, but as soon as that instant pass, we are going to get an exponential decay in the voltage across the capacitor, and it will decay exponentially by a factor of Rc. Okay, and we are going to see that plot in a second as well. Okay, so moving on. Again, this is the voltage of the capacitor. Again, this V of t is Vc of t. This is what we are looking from the book as well. Book has a expression Vt as I've shown you in the circuit, and I derive this equation Vc of t just to differentiate the voltage across the resistor and the voltage across the capacitor. But this V of t is a Vc of t. Okay, and again, this V naught is essentially your V naught or Vg. Again, capacitor voltage, right? So V naught equals to Vg and V naught. Again, I'm making this point again. Of course, I'm going to stop making these points again and again as we're going to move forward, and so I'll just stop repeating some of the stuff. Once the capacitor gets charged, the capacitor becomes an open circuit. So before switching or taking out the excitation source at time t equals to 0, just before that instant and after that instant, your capacitor is going to is going to not allow an instantaneous change in the voltage, and the voltage across the capacitor will remain equals to the V naught or Vg. Right, so V naught denotes the initial voltage in the capacitor, and of course we have a time constant which is RC and represented by tau. So we have a time constant equation. Sorry, what happened? Okay, and here's the natural response of an RC circuit as we derived here in the previous slide. Okay, so I'm going to show you some of the curves now. This is yeah, we talked about this. Here is a voltage curve with respect to time of the capacitor once we remove the excitation source. And again, this is a natural response of an RC circuit. If you see this curve, the blue one, or yeah, the dark bluish one, this curve decays exponentially. At time t is equal to 0, your initial voltage is V naught, as we discussed over here, as we know from this equation, this V naught, right? At time t equals to 0, you're going to get the capacitor voltage is exactly equals to the V naught. However, then the exponent is going to come into play, and this is going to increase by this equation, and by this value tau equals to RC. We did a very similar analysis of this line, of what this black line is, in case of the inductor current in the past lecture. So I'm going to just repeat the similar analysis here without going through all the derivation, right? We saw that what is going to happen is right after, at time t equals to 0, right after that, at time t equals to 0 positive, right? How much is the rate of change of the voltage, capacitor voltage, right? This rate of change is determined by the slope, and the slope is minus V naught over t, right? So essentially dVc over dt at time 0 positive is minus V naught over tau. And so this is a slope of this line. So if you're going to plot a tangent, it is going to cross that time axis at time t equals to tau. And of course, we can write this linear line following exactly the same process, y equals mx plus c, as we did in the past lecture. So again, this is very similar looking plot as we did for an RL circuit. The blue line represents the real change on how the capacitor voltage decays over time, or the capacitor discharges itself through the resistor R. And the black line represents this kind of a hypothetical scenario that if your capacitor voltage will continue to decrease by the ratio of minus V naught over tau, then of course it is gonna flatten out much sooner, exactly at time t equals to tau. Right. However, if you consider the real case scenario of this blue curve, we already know that at time t equals to 1 tau, you approximately get 37% of the V naught. At time t equals to 5 tau, you get like less than 1% of the V naught, and it will take approximately infinite to get you to exactly 0. But beyond 5 tau, for practical considerations, you can consider a steady state to be reached. Okay, moving on. So here is our natural response of an RC circuit. We have defined this V naught as the initial voltage, and this is the exponent which defines the decay of the capacitor voltage over time at this. Okay, here are the 4 steps that are written up, very similar. Essentially, you don't need to remember it. All you need to do is to find the value of the V naught and tau. So your step number 1 is essentially asking you, whenever anybody asks you to find the natural response of an RC circuit, the very first thing to do is to find the value of the V naught. And how do you find the value of the V naught? Again, the value of the V naught represents the initial voltage across the capacitor. And where is that voltage coming from? That voltage is coming from the original, before time t equals to 0, whatever the source was that was charging the capacitor to its value. So this is how you can find the value of the V naught. And depending on what other resistors are there. Right, so you have to analyze the circuit at t equals to less than 0. In the second step, you have to find the value of the time constant, RC. If you have multiple resistors there, find the equivalent value of the resistance. So you are going to draw the circuit at t is greater or equal to 0, and then find the equivalent resistance. and the capacitance, and find the time constant RC. Once you find both of these values, put both of these values over here, find this equation V of t. And similarly, if you have to find any other parameters of the circuit, for example, the current through a circuit, or if there is other resistors, the power dissipation energy, find all of those parameters of interest as well. So don't worry about the steps, just remember this equation and know what is V naught and what is tau. Okay. We spent quite a lot of time in deriving the expressions of the various expressions of the energy and the power in case of an inductor on RL circuit. So I'm not going to do this entire exercise again. Very briefly, however, I am going to write down the expressions of the rest of the parameters, right? So this is again the natural response of an RC circuit. For example, what is the value of the current that is going to flow, right? And again, I of t is equals to vt of r. So we can easily divide this. I think we already write down this expression, but minus t over tau. And this expression is going to be t is greater or equal to 0 positive. Again, why it is equals to greater or equals to 0 positive, right? Because again, this is a current that is going to flow through a circuit. At time t equals to 0, there was no current flowing because capacitor was an open circuit, was behaving like an open circuit. At time t equals to 0, capacitor was an open circuit, so there was no current exactly at the instant t equals to 0. And right after that instant, of course, the distorting process, you can assume that the distorting process has started and the current has started to flow. So current only makes sense. Current and the power through the resistors dissipated in the resistors, and the energy consumed by the resistors, all of these following parameters only make sense at t equals 0 positive. Beyond, okay, so this is what we get for I of t. Similarly, we can find the power P. We know that power equals to V of I. And again, you have a value V here and I here, so you can multiply both of them. So you get V naught squared over R e raised to power minus 2t over tau. This is also valid for 0 positive. Similarly, you can find the energy represented by W, and we did this in detail again in the previous lecture, so I'm not going to go through it. Essentially, you find the value of the energy by integrating for a time t power, right, and dx. And we derived a very similar expression in the past lecture for an inductor, so you can review that lecture to see how we drive this thing. And the answer that you will get is half c v naught square 1 minus e raised to power 2t over tau, right? So how we get from this to this, we have already done that. Look at the previous lecture. T is greater or equal to 0 positive. Okay. Okay. So I have all of these equations written over here as well, but they represent exactly the same thing. Okay. So these equations are very important because you can potentially use these equations to find the rest of the circuit parameters or the questions that are being asked in the circuit problem. So let's do our example problem now. Okay, so this is kind of a very beautiful example. You have this good circuit. Okay, so what is happening in the circuit? So if you look at the switch closely, let's read. Why don't we read it? The switch in the circuit shown above has been in position X for a long time. At time t equals to 0, it moved to Y, right? So this is position X and this is position Y. So at t equals less than 0 time, the switch was in position X. This means that the capacitor was connected to the voltage source. If the capacitor was connected to the voltage source, then the capacitor was being charged. And if it was connected long enough, means more than 5 tau, then the capacitor got charged. Okay, so if the capacitor got charged, then we know that at time t equals to 0, exact time t equals to 0, when the switch moved from position X to Y, and this excitation source got out, the capacitor is going to still behave as an open circuit, and the voltage across the capacitor VC should be equals to 100 volts. I'm going to make it a point again in a second, right? But the excitation source got removed, and then we get the right hand side of the circuit. Okay, so let's solve all of this. The question asks you to find the capacitor voltage at time t is greater or equal to 0, the value of the V naught, which is the voltage across this 240 kilo ohms resistor, and the value of the I naught, which is a current that is going to flow over here through 60 kilo ohms resistor, and the total energy dissipated in the 60 kilo ohms resistor as well. All right, so let's solve this thing. Okay, great. So, oh my God. Okay. So let's solve for solution. Okay, so solution, I am interested in solving for one, which is a capacitor voltage at time t is greater or equals to 0. In order to find the capacitor voltage, again, if you remember, all I need to do is to follow those 4 steps, and those steps includes that, practically includes that the step number 1 was that find the value of the V naught, or the initial capacitor voltage at time t is less than 0. So let's draw the circuit when before time equals to 0 or time t equals to 0, right? So we know that when the circuit was at position X, essentially you have this battery, you have a resistor, and you have a capacitor, right? So you have 100 volts, this here, 10 kilo ohms resistor over here, and here you have a capacitor C, right? So the voltage across the capacitor, once that capacitor gets charged enough, right, this was a initial voltage across the capacitor, V naught. So, and we know that from our previous lecture, one of the recap lectures, that this circuit will charge the capacitor all the way to 100 volts. So your V naught will become 100 volts. And the capacitor is going to behave as an open circuit, right? So practically speaking, this is how your circuit is going to look like. Plus minus V naught, 100 volts, and 10 kilo ohms resistor. Okay, so this is a circuit for t is less than 0. Okay, if this is a circuit, then we can find the value of the V naught to be 100 volts. Okay, so this is good. Then let's do step number 2. Step number 2 asks to find the value of tau equals RC. In order to find this value tau equals to RC, we need to solve the circuit for t is greater or equal to 0. So t is greater or equal to 0 means that the switch now has been moved to position B. So let's redraw the circuit at position B. So we get a capacitor over here, we get a resistor over here, we get another resistor over here, and another resistor over here. Right, so this is 240K, this is 60K, this is 32K, and we have a capacitor 0.5 microfarad. Okay, cool. This is our circuit for t is greater or equals to 0. We also know that the current I naught is flowing over here. The voltage across here is V naught, and the voltage across here is VC. Okay, great. So this is our circuit, right? And we need to find the value of the T and RC. We already know the value of the capacitance, 0.5 microfarad, but we don't even know the value of the resistance. If you remember correctly in our discussions, that in order to find the value of the resistance and the tau over here, we need to find the value of the R equivalent. So what is the value of the R equivalent over here? We know that these two resistors, 240K and 60K, are in parallel, right? 240K and 60K are in parallel. And the parallel combination of that would be in series with 32, right? So I can easily write this thing by 32K plus 240K in parallel with 60K. So if you were to solve this, you are going to essentially get to the R equivalent is going to come out to be 80 kilo ohms resistance. So you can easily find the value of the tau, which is R times C. So you get, essentially this is R equivalent times C. So you get 80,000 ohms times 0.5 microfarads. So your value of the tau is going to come out to be 40 millisecond. right? And if in terms of seconds, I can also write this 0.04 seconds. Okay, so once I got both of these things to find the value of the V naught, once I found the value of the V naught and the value of the tau, all I need to do is to put both of these values in the equation, in the capacitor equation of the natural response. So I am going to do that. Again, so if you remember, the capacitor equation was V naught e raised to power minus T over RC or T over tau, right? I already know both the values, so VC of T should be equals to V naught. V naught is 100 volts, e raised to power minus T divided by tau is 0.04. 0.04. Another thing that we can do is we can also do 1 divided by 0.04 is 25. So I can further write this thing to make my life easier as 100 times e raised to power minus 25 T volts, right? And again, this is valid for T is greater or equals to 0. This is a capacitor voltage. Okay, nice. We got this. Now the second, let's solve for the second one. The second one is V naught of T, which is a voltage across a 240 kilo ohms resistor, right? This one. And of course, this is only going to be valid for 0 positive because at 0, the capacitor is an open circuit. And if the capacitor is an open circuit, no current is going to flow through it. Flow through 240 kilo ohms resistor. Okay, so let's do B. What do we have to find in B? Again, we have to find the voltage V naught of T for T is greater or equals to 0 positive. So let's find this out. Okay. Let me, either I can redraw the circuit or I can constantly, I need to get back. Okay, so here's our circuit. If you look at the circuit and I need to find the value of the V naught over here, if I know the value of the VC, why don't I redraw the circuit 240K and 60K? Maybe it's going to make life easier. Okay, so here's your capacitor voltage, resistor, another resistor, right? 60K, 240K, 32K. This is VC. This is plus minus V naught, and this is I naught. Okay, great, right? Again, we talked about, the first point is that we talked about why this is only valid for 0 positive because V naught at 0 negative was equals to is 0 and open circuit is 0 or open circuit. Oh no, sorry, it's not open circuit because there was no current that was flowing. Because you have an open circuit at the capacitor, not at the output voltage here, across 240. Okay, let's find the value of the V naught. Again, your V naught is appearing over here across 240 kilo ohms. So I can simply use a voltage divider rule. Okay, so if I will use a voltage divider rule over here at 240 kilo ohms resistor, right? And if you remember, voltage divider rule, if you are interested in finding the voltage at a particular resistor, if two resistors are in series, then essentially what you need to do is you need to figure out what's your or the voltage are, the initial voltages, which is VC of T, and then you have to multiply it with the resistor across which you are interested in finding the voltage, which over here is a parallel combination of our 240 and 60K, right? Because V naught across 240 is the same as a V naught across 60K. So this is going to be a parallel combination. So essentially you're going to have our 240K in parallel with 60K divided by both resistances summation, which is 240K in parallel with 60K, and again in series with 32K. So this should come out to be, if you were to solve this, right, if you were to solve this resistor combinations, this is going to come out to be 0.6 VC of T, and I'm going to replace VC of T as well, right? So this entire combination is going to come out to be 0.6. So 0.6 times VC of T, 0.6 VC of T is 100 e raised to power minus 25T Um, so zero point 0.6 into 60, 0.6 into 100 is V naught. V naught of t is 60 e raised to power minus 25t. And again, this is valid for 0 positive. This is the value of the V naught here. Okay, great. So we ended up finding the value of the V naught of t as well. 60 e raised to power minus 25t. Okay, what's the third thing that we need to do? We need to find the value of the I naught now. Okay, so let's do C part. C part, we need to find the value of the I naught. And again, this also makes sense for 0 positive because no current was flowing exactly at 0. The capacitor does not like the change in the current instantaneously, does not like the change in the voltage instantaneously, and that is why it is going to behave as an open circuit. Inductor doesn't like the change in the instantaneously in the current. Okay, so we have an I naught of t, and again we can easily find I naught of t, which is flowing through the 60 kilo ohms resistor, right? So I naught of t is equals to V naught of t divided by R, which is 60 ohms. So this is 60 e raised to power minus t times 25 divided by R is 60k. So you practically get 60 divided by 60, and 1000 is going to come up. So I naught of t is going to become e raised to power minus t. Sorry. Oh man, what is happening? E raised to power minus 25t milliamperes, right? This 1 over k becomes 0.001 amperes, so it comes out to be milliamperes. And again, this is for t 0 positive. Okay, let's do part D now. Part D was the total energy dissipated in a 60 kilo ohms resistor. So we are interested in finding how much energy was dissipated in the 60 kilo ohms resistor. Whenever you have to find the energy dissipated, start with the power dissipation. Okay, so what is the power dissipated in 60 kilo ohms resistor? Okay, so let's do that. So power 60 kilo ohms resistor is, I can simply do, for example, I square R, I naught square of t times R, and I naught square is pretty easy, which comes out to be e raised to power minus 50t, right? E raised to power minus 50t. Okay, times R. R is 60 kilo ohms, right? So you get 60 k milliwatts. So P 60 k times T comes out to be a total of 60 e raised to power minus 50 t milliwatts. Okay, so I naught square is in milliamps, right? And the resistance is in ohms. So in order for it to become milliwatt, the resistance needs to be shown in milliohms, right? So this is going to come out to be 60 or 60 kilo ohms, sorry, right? So 60 kilo ohms. So the total power dissipated in a 60 kilo ohms resistor is going to come out to be 60 e raised to power minus 50 milliwatts. And again, this is also only valid for 0 positive. Okay, so we ended up finding the total power that is dissipated in a 60 kilo ohms resistor. Now we are going to find the total energy dissipated there. Total energy dissipated would become, again, we know that it is from 0 to infinity whenever we are talking about total energy dissipated, right? And we do essentially power times dt. So power is 0 to infinity. And again, I can do exactly the same thing, which is going to come out to be essentially 60 e raised to power minus 50t, right? And again, if you remember, we solved this thing 0 to infinity e raised to power minus, for example, 50t should come out to be 1 over 50, right? So you can use this thing to figure it out, that you are going to get 60 over 50, and this is going to come out to be 1.2 millijoules. So this is the total amount of the energy that is dissipated in the 60 kilo ohm resistor. Okay, so with that, this is pretty much the end of the natural response of an RC circuit. Again, I am going to make a quick a review of what we learned in this lecture. Just a 1 minute. Probably it's kind of a new thing that I'm thinking of starting, right? So we started with the natural response of an RC circuit, where we said that, for example, over here, that before time t equals to 0, the capacitor was being charged, right? So once the capacitor gets charged, capacitor becomes an open circuit. So when it moved at time t equals to 0 to a position B, and the excitation source was out right at that instant, the capacitor was still open circuit, and the initial voltage across the capacitor was V naught, right? And that V naught was exactly over, in this particular case, is VG, or whatever the source voltage is, right? So that is why the capacitor voltage can be defined for t equal or greater than 0, but for the rest of the things, for example, the energy dissipated and everything is defined usually for 0 positive, because that at that instant the capacitor is open circuit. Okay, so we learned that. Then we essentially very simply drive the equation of the capacitor voltage, coming out to be essentially this. Vc of t equals v naught e raised to power minus t over tau. So please remember that. And then over here again, this is a current. Again, this is only relevant for 0 positive, because at 0 nothing was flowing, because the capacitor was open circuit. And then we ended up defining time equals RC. We also looked at the natural response capacitor voltage curves, and this is the natural decay, which depends on the value of the tau. This is that hypothetical scenario if right after the switching at 0 positive, the slope of the curve is minus v naught over tau, and if it continues to decrease by that, in that hypothetical scenario, it is going to cross the x-axis at time t equals to tau. We looked at that. Then we essentially look at, here are the 4 steps that you can use to find the natural response, and at the heart of it, don't worry about the 4 step. You need to just find the value of the v naught and value of the tau. We looked at all of these equations, and again, in all of these equations, they all make sense at 0 positive, because at time t equals to 0, capacitor is an open circuit, right? Then we did this example, and this was a very simple example, and I hope you will remember how to solve this thing. Okay, so great. This is pretty much it on the natural responses. In the next lecture, we are going to start with our step responses. So first, we're going to do a step response of an RL circuit, and then we're going to do a step response of an RC circuit as well. All right, thank you so much. Have a great rest of the day. Thanks, bye.